radio wave, if you think in terms of photons, now that concept of photon is actually applicable to all spectrum of EM wave. All spectrum, including radio wave. So you think in terms of the radio wave transmitting energy in bundles, and each bundle called photon, its energy is hf. So knowing the frequency, therefore you can find energy. And now conveniently, we always convert it into electron volt, which I explained to you before, remember? Electron volt is the sub-energy of joule. It's 1.6 times 10 to the power minus 19 joule. That's how much is 1 electron volt. So divide by this amount, you get the energy in electron volt. And we are asked to find how many photons emit per second. So I take the power emitted divided by the energy of each particle emitted. Then that ratio will give me the number of photons emitted per second. Next, if this is now not radio wave but visible light, 633 nanometer, what's the photon energy? The photon energy is hf or h over lambda. If you convert it into EV is 2 EV. And if we have the same number of particle photon being emitted at this energy, what is the power output? You just take n number of photon emitted, multiply the energy of each photon. That will give you how many joule emitted per second. So it's in watts. Okay? Now this question, if you just look at it from the perspective of a maths question, actually there's nothing special about it. But it does reveal something if you take a look carefully. We say that especially for visible light, for X-ray, all these, for ultraviolet, infrared also, we treat light as photons. Why? But when we talk about radio wave, you seldom deal with photon. If you talk to people who are in communication, they are generating this wave, you tell them photon, they'll be very blurred. Why are you talking about photon? But in fact, the photon concept is applicable, but we don't usually talk about photon in radio wave, right? Or in microwave and so on. Why? You look at the answer here. The photon energy of visible light is 2 electron volts. And 2 electron volt is actually quite substantial in the microscopic scale of how the photon can interact with material and so on. But if you talk about photon energy in a 100 megahertz wave, the energy is how many orders smaller? Right? If you ignore the first term here, it's about 7 orders smaller. What does it mean? It means that in a radio wave regime, the energy, if you consider photon, the energy of each photon is so small that it's almost continuous. Is there any meaning talk about quantization? No. You know what I'm trying to say? Because this energy is so small, 10 to the power minus 7 as compared to visible light. So therefore, this energy, when you talk about any reasonable amount of energy, it involves a huge number of photons that the concept of quantization has no meaning anymore. Is it clear? So this is something that I believe what this question is trying to elucidate. That means that in radio wave, because the energy is so small, talking about quantization of energy has not much meaning. Whereas in visible light, there is a lot of meaning because several EV is quite a substantial amount of energy. And just for information, in fact, currently the technology is so advanced that we can measure photon one by one. They are what we call a single photon counter. They are instruments whereby they can count how many photons being received. So this is how we can actually measure precisely. But if you talk about electromagnetic wave, it's very hard to measure because the energy is so small and it comes in such a huge number. So this is as good as a continuous quantity rather than a quantized quantity. Is it clear? Okay, question 2. Black body radiation.